Hello everyone, this is Professor Rivera. I am going to be going over chapter 2, and this is the second video where I'm going to talk about the different parts of the nervous system, and then I'm going to talk about the different parts of the brain and their function. The nervous system, we're going to talk about both the central nervous system and the peripheral nervous system. The peripheral nervous system is all of the nerves in the body that sort of react to the environment. Now, the nervous system is quite complex. You have your central nervous system and your peripheral nervous system. In both, there are neurons or nerves that are going to the brain, coming from the brain, and they are being analyzed by different parts of the brain. Sometimes two signals are sent at the same time to do one very simple thing. For example, if you put your finger up, right, hold your hand in a fist, and put your index finger up, right, you would think that in order to do that, your brain sends one signal to your index finger to release or to go up. But that's not the way it happens. There are layers of signals being sent. So there is a signal being sent to your entire hand to open, while at the same time, GABA blocking neurotransmitters or a blocking signal is being sent to your pinky, your ring finger, your middle finger, and your thumb, so that those don't react to the full signal, and only your index finger stands up. That is quite complex. Why would our system sort of be created like that? Well, because the ability to move your fingers independently of each other, that's something that evolved late in the evolution of the hand. And so we can do that, but very few other animals have the ability to do that, to use our fingers separately. But we had to use what came before. And so essentially just a new layer of complexity was added onto it. It's kind of like if you have a program that, let's say Microsoft Word, and you want to make it better. Well, you could just start from the beginning and just create a completely new system, or you could take the system you already have and add more codes, more complexity, more lines of programming. And sure enough, that is the way it is done for both Microsoft Word and for the complexity of our behavior and our cognition. And so let me first talk a little bit about nerves coming and going. So sensory neurons are also called afferent nerves. These are nerves that begin in the body and they send information to the brain. For example, my eyes get information from the environment. My eyes are in my body and they send information to my brain via my optic nerve. My optic nerve is a sensory neuron. My ears hear information or some signals from the environment, and they send that information to my brain via my cochlear nerve. My cochlear nerve is a sensory neuron. So whether I'm talking about the sensation of touch in my hands, in my skin, or my tongue tasting something, all of that information must go to my brain via afferent nerves or sensory neurons. Now, the opposite is happening once my brain analyzes whatever it's analyzing, and then it makes a decision, and then it tells me to grab that drink in front of me or to spit out that piece of food that's in my mouth, let's say. Um, that that control over my body is occurring through efferent nerves, or what we call motor neurons. That is, my brain is telling my hand how to move via efferent nerves or motor neurons. It's telling my mouth how to move. Now, efferent nerves are both somatic, that is voluntary, and autonomic, that is involuntary. So movements like my heart, my breathing, most of my breathing, whether my uh, the arteries or the veins in my body expand or constrict, whether my eye dilates or constricts, all of those are involuntary movements, but it's still my brain telling my heart, my uh, arteries what to do. Um, and so that's still efferent nerves. And now, if I'm talking, if I'm walking, if I'm riding or driving my car, these are voluntary movements. And it's my brain telling my body what to do. But it's still efferent nerves, whether it is voluntary or involuntary movements. The last thing you see there are interneurons. And interneurons we sometimes call white matter. These are the connections within our brain and spinal cord. So that, for example, I'm looking at the screen. Well, that's my occipital lobe creating that picture of the screen. But my frontal lobe needs to know what's happening. Um, and so I need to know that this screen is for class, maybe, what is the purpose of sitting here? What does it all mean in the grand scheme of things? Well, a lot of those things are going to be analyzed by the frontal lobe. Well, my occipital lobe needs to send the information to my frontal lobe. Well, the wires, the neurons that go from my occipital lobe to my frontal lobe, uh, those are interneurons or white matter. They help the connections, they make thinking and processing information possible. Now, this reflective arc where sensory information is sent to the brain via afferent neurons, and then the brain analyzes that information, sends it back and forth throughout the brain via interneurons, and then it controls your body's movements via efferent neurons. We call this the reflective arc or the reflex arc because it's happening, and then the whole process happens over again. As I grab that soda, that cup, I know that it's cold. Well, that's sensory neurons, afferent neurons again, being sent to my brain. So the whole process is sort of an arc. It goes back and forth, back and forth. Now, what you're seeing here in front of you is the division of the nervous system. And I will make a point that this will show up quite possibly in a test. So it is something to kind of memorize and understand. Now, the first division here is between the central and the peripheral nervous system. Your central nervous system, this is your brain and your spinal cord. Your peripheral nervous system, think of that mostly as movement. Voluntary movement, we call somatic nervous system. Involuntary movement, that's the autonomic nervous system. And your autonomic nervous system also has two systems. A system that we call the sympathetic nervous system. This is active, on. You can think of it as on. This is your heart beats faster, you're breathing more deeply, maybe you're sweating. Um, this is on, fight or flight. And then there's also the parasympathetic nervous system. This you can think of as off or low. Now you're calm and relaxed. Your breathing is more shallow. Your heart is slower. Your eyes are probably constricted. Maybe there's a chance you feel tired. When you think about the central nervous system, think about it in terms of what's happening in the mind and brain. These are your thoughts, your feelings, your thinking, your analysis. If I tell you that Joe is taking a test and he's very nervous, and then I ask you, what's happening in Joe's central nervous system? Well, you're going to tell me what's happening in his mind. Joe is doing the test. He's figuring it out. He's problem solving. He's remembering. He's using logic. All of these are thoughts. Maybe he's scared or he's afraid that he might fail. These are feelings and emotions. Things that happen in your mind, they're happening in your brain. That's your central nervous system that's doing that. Um, your peripheral nervous system, on the other hand, think of that as a movement, voluntary movement, involuntary movement. In either case, it's your peripheral nervous system that moves your body. Now, your peripheral nervous system, part of that is the voluntary part, your somatic nervous system. This is everything that you do that's voluntary: speaking, writing, um, running, driving your car, riding a bike, right? All of these things, you are making the choice to take notes. This is somatic. When I ask you about Joe taking that test and I say, what is happening in Joe's somatic nervous system? You're going to tell me that he's writing down the right answer, or maybe he's reading and his eyeballs are moving across the page. That is somatic. Now, if you tell me that he's understanding the words that he's reading, that's not somatic. That's the central nervous system. That's knowing and understanding. But the movement of his eyes, that is somatic. Okay. And as I mentioned, your autonomic nervous system um, is involuntary, but there are two parts there: the sympathetic and the parasympathetic. Your sympathetic nervous system, you can think of this as fight or flight, right? You probably heard that phrase before. The fight or flight response. There's a lion in front of you, and you have to make a choice. Am I going to fight this lion and get eaten? Or am I going to run away from this lion and probably get eaten anyway? Um, this is, in either case, whether you decide to fight or to flee, your body kind of prepares in the same way. Your pupils dilate to let in more light so you could see better, take in more information. Your saliva is inhibited. This is no time to have a chip while a lion is chasing you. And so your saliva gets inhibited, but your heart speeds up, your breath becomes deeper, it becomes faster. And the one thing that gets turned off is your digestive system. I told you just a moment ago that you could think of your sympathetic nervous system as on because almost everything else is getting turned on. Pupils get more dilated, your heart speeds up, your breath gets faster, blood is being pumped to your arms and legs, to your limbs, but everything that is to do with your digestive system gets shut down. Saliva, digestion, because this is no time to digest food while there is a chance that something might eat you. Now, this presents problems, right? Obviously, if it's a lion in front of you, or if you're in a literal fight with someone, this holding off of the digestive system is really good because you need to fight, you need to uh, get this problem out of your way. And your digestive system uses too much energy. And so if you're trying to digest a sandwich while you're trying to fight a lion or a person or whoever, you're going to lose because your digestive system would be pulling too much energy. Now, the problem is that because we live in the world that we do, a lot of our stressors are social. And so sometimes we turn on our sympathetic nervous system because the person that sits next to us was a little rude, and this will ruin now our digestive sort of intake or our digestive system for hours because we're a little upset about something someone said. Let me give you another example here before I move on. Every once in a while, maybe you're at work or you're doing homework and you're super into it, and you don't eat. You're not even hungry. You maybe don't even you haven't gone to the bathroom for a while, and you just feel super excited, or maybe just scared, and you're super into it. And then you decide to quit. The day's over, or you're just taking a break, and immediately after you stop being active, what happens? You realize you're starving, or you realize you have to rush to the bathroom. Why? Because immediately when you took that break, you shifted out of sympathetic nervous system and you shifted into parasympathetic nervous system. And now you're in a relaxed mode. We call this rest and digest. So fight or flight versus rest and digest. And here, your pupils constrict. You might feel tired. You might start the stimulation of tears. It's a great time for a cry. You're going to stimulate saliva, and your digestive system turns on. This is a great time to have a chip, to digest that sandwich that you ate, because you're not doing anything, you're relaxed. And so now if your digestive system turns on, then you have the energy to do that. But in the prior example, where you hadn't been eating for quite a while because you were super busy doing work or doing homework, well, now you're relaxed, and now your digestive system turns on all at once, and you have to rush to the bathroom, or you realize you're starving and you have to get something in your mouth right now. You might notice that every once in a while you're in class and you just went to the bathroom, but you're in class for like 5 minutes and you're like, I have to go to the bathroom now. Um, or you just ate, but you're in class and now you're like, oh, I'm going to finish this Snickers because I'm starving, it feels like. This is because when you're in class, a lot of times you're a little bored, and your digestive system turns on because you're in parasympathetic mode. You'll notice that the opposite is true of your teacher. It's very rare that your teacher has to stop class in the middle of class and go, oh, guys, stop. I have to go to the bathroom, or I have to eat the sandwich right in front of you, because your teacher is doing a lot of things. She's thinking about what's happening. Are my students understanding? Are they listening? Does this example make sense? Did this joke go over well? And so your teacher is actually in sympathetic mode while she's teaching. Um, and so she very rarely has to go to the bathroom in the middle of class. Whereas students almost always have to go to the bathroom in the middle of class. Here's a quick list that you can kind of go over the different parts of the body and whether um, what happens to them when they are in sympathetic mode versus parasympathetic mode. Okay. In this part, I'm going to go over the parts of the brain. And I'm going to specifically talk about this part does this and that part does that. But first of all, I want to go over sort of some divisions. Um, the first division you see there in red is the brainstem and the cerebellum, which, which we often call um, the brainstem, and this is your hind brain. You share this with almost everything that is an animal, including fish and reptiles and birds, amphibians, and obviously mammals. Almost everything that is an animal that moves is going to have a brainstem. Not everything. Sea stars that move, they don't have a brainstem. Uh, but almost everything you think of as an animal is going to have this. Without this, there's a good chance you're going to die. Now, in that light purple slash lavender, you see the limbic system. And your limbic system is a lot of how your memories are controlled, your emotions, a lot of habits, especially physical behavioral habits. You're going to share this with things like reptiles and birds, and obviously other mammals. Um, and then your neocortex, which is usually what we think about when we think about the brain, is all that wrinkly part. Uh, this you share with birds and other mammals. Reptiles have small portions of neocortices, but they're not by any means as large as ours or as mammals. Now, what you're seeing here is the difference in the frontal lobe between a human and a cat. In the cat, you'll notice that a cat obviously has a frontal lobe, but their frontal lobe is not as thick, is not as large as ours. Um, it's so small, in fact, that it doesn't even cover the brainstem completely. You can still see the cat's brainstem sort of in front of the frontal lobe. But the human brain isn't like that. The human brain, the frontal lobe is enormous. This is in a lot of ways what makes humans humans is this large frontal lobe. Now, let me start here with the hindbrain. Okay. Uh, in the hindbrain, you have your medulla, and your medulla, here is your brainstem, okay? And it's kind of the lower portion of your brainstem before you get to the spinal cord. Without your medulla, you would die. Is your medulla that keeps you alive. It controls all of your vital bodily functions, including breathing, your heart rate, a lot of your reflexes. If you damage your medulla, it is very difficult for you to stay alive. Um, Non-fatal damage, so that's going to be like partial damage to a specific part, might include things like numbness, paralysis of a whole chunk of your body, difficulty swallowing, for example. Um, Now, it's very complicated to think about each part of the brain, this little chunk and that little chunk. So I often like to include little characters that help you to remember. And I think of my medulla as the doctor of the brain because it's your medulla that keeps you alive. It controls your heart, it controls your lungs, and all the things that your doctor usually looks for to make sure that you're staying alive. Now, if there's a doctor of the brain, then there has to be a nurse. And your nurse is going to be your pons. Your pons were still here in the brainstem. And you'll notice that there's this little piece that kind of sticks out like a belly, like a fat belly. That's your pons. And your pons also regulates certain vital functions, motor control, sensory analysis, including sleep, arousal, involuntary breathing. If you were to damage your pons, there's a good chance that you're also going to die. Uh, when you damage it in mild ways so that it doesn't kill you, it's still incredibly dangerous. For example, you might become unable to breathe unconsciously. So now every single time you breathe, then you have to think about it. There's never going to be a time when you're not thinking about it and you're just breathing automatically. Your pons controls that, and without your pons working correctly, then all of a sudden you can't do that anymore. As I mentioned, my pons here is the nurse because she checks up on you and does a lot of the heavy lifting of keeping you alive, making sure that all the sensory stuff works, making sure that you're breathing while you sleep. This is our nurse of the brain, your pons. Now, if you look right behind the brainstem, there's this slight spongy piece that is called the cerebellum. The cerebellum is kind of like the athlete of your brain. This is still part of the hindbrain, but this helps you with coordination and balance. things like playing a sport, jumping around, spinning, but also simple things like, getting your pencil to get on the line as you write, hitting that key on your smartphone so that you hit the letter that you want. This is part of coordination and balance. And if you were to damage your cerebellum, you would be damaging that. You would lose coordination, inability to judge distances, inability to perform rapid movement changes. So, for example, let's say that I'm studying and I'm writing something and then I'm changing to look through the book to find a specific thing, right? Well, that change of movement from writing to looking through the book, shifting pages, that would be very difficult to make that change rapidly if the cerebellum is destroyed. Um, uh, Other movements would be messed up, a staggering or a staggered walk, a wider stance, because obviously balancing would become difficult. Now you'll notice that my characters there are an athlete, a dancer, because obviously the quick movements, the changes in movement required a great deal of balance and coordination. Now, your reticular formation is right behind the pons. This is still your brainstem. And remember, I told you your pons is this little belly that sticks out of the brainstem? Well, your reticular formation is right behind that. And it controls your ability to pay attention and to ignore things, which we call the reticular activating system. Essentially, it is your ability to focus on things that are interesting or important and not pay attention to things that are not interesting or are not important. Think about you being at a party. There's music, there's people talking all around you, but you're talking to one person. If you were paying attention to everything, to the music, to the lyrics of the music, to the people talking next to you, it would be very hard for you to pay attention to and understand the person you're speaking with. And sometimes you'll say things like, "Oh, I just ignore. My ears aren't paying attention." But your ears can't do that. Your ears aren't smart enough to quote unquote not pay attention. Your ears take in all of the stimulus, including the music and the people talking and the lyrics and the melody, and someone dropped a plate in the distance. It's all of that gets sent to your brain. It's your reticular formation that makes decisions. It's your reticular formation that says, this is not important right now. Don't pay attention to this. This conversation, this is important. Send this to the frontal lobe so that we can pay attention to it and understand what it means. Send it to the Wernicke's area so that we can understand the language portion. Um, and so your reticular formation helps you to pay attention, but it also helps you to ignore the music, etc. If you've ever tried to teach, I don't know, a third grader long division, and after you're explaining something, you notice that they're paying attention to like a bug in the window, and you're like, pay attention to me. Um, what's happening is that they haven't learned to control this just yet, right? There's certain things that your reticular formation is going to pay attention to naturally. Something that's loud, something that's large, if it's colorful or very different, unique. These things are easy to pay attention to because your brain kind of comes pre-programmed to pay attention to those things. And there's some things that are easy to ignore. Someone talking about something boring. For example, someone teaching you long division or about the reticular formation, right? After a little while, the voice gets, monotoned and it's kind of all the same thing, and it's very easy for you to ignore that. But one of the things that you try to do and that you try to learn as you get older is to not let yourself lose focus on things that overall might look boring, but in fact are important. And so you have to continue to pay attention to them, like long division or the PowerPoint that you happen to be reading for class. Now, the reason I chose Deadpool as my character is because Deadpool does something that most characters don't, which is sometimes he notices the audience. And so he'll ignore what's happening in the movie or in the comic book, and he'll talk to the audience for a little while. And then he'll do the opposite. He'll ignore the audience and go back to paying attention to what's happening in the movie, right? Essentially, Deadpool's reticular formation has the ability to pay attention to the audience and go back and pay attention to the movie. Again, your reticular formation allows you to pay attention, but also ignore. Now, I want to talk a little bit about the limbic system. Your limbic system is in the center of your brain. So you're seeing the brain here kind of split in half, and the limbic system is right in the middle. And everything that's on the left-hand side is also going to be on the right-hand side. So there's it's just like your neocortex that has two parts to it. Um, your In your limbic system, the first part that I want to talk about is the amygdala. And your amygdala is this little reddish almond-shaped sort of ganglion. And your amygdala helps you with emotions, specifically strong emotions like excitement, fear, anger, anxiety, and memories about fear and anxiety. So let's say that when you were a little kid, you got stung by a bee. And so now you're afraid of bees, right? Your amygdalas don't remember the time that you got stung by a bee. It's not like the memory is in there. Your amygdalas remember how to react to that. And so if you see a bee, now you're an older person, you see a bee, your amygdalas turn on the correct reaction. That is the fear reaction. And so sometimes people see memories and they think like, oh, I remember, memories like I remember the one time that this happened. No, not those kind of memories. Your amygdala is memories about the reaction. If you were to damage your amygdala, then you would lose the ability to feel emotions correctly. You might forget or not react appropriately. Um, Research suggests that people who have minor damage to certain parts of the amygdala don't know how to assess risk correctly. And so they'll take big risks for things that have very little payoff. The character I chose here is an elephant because you might have heard the phrase, an elephant never forgets. And your amygdalas are like that too. Let's say that you got stung by that bee when you were 5 years old, and then you never saw a bee again, never even read about a bee in a book. But now you're 23 and you see a bee again. Well, your amygdalas remember that you're supposed to be afraid of bees, and they will trigger the fear reaction. Even though you don't remember the time that you got stung by a bee in this hypothetical scenario, you don't even remember what a bee is because you never learned about it in school. But your amygdalas will still remember that you're afraid of those things, and it will trigger the fear effect. And so that is why I chose that an elephant never forgets. Um, Now, your hippocampus, if you look at this little green ganglion, it looks like a little worm. This is your hippocampus. And again, you have two, one on each side of or each hemisphere, and it's located in your limbic system. And this is how you control the creation of memories. Now, if you are a bird or a crocodile or a sea turtle or even a person, there are a few memories that are actually located in the hippocampus. And those are specifically memories about spatial memory. So, for example, sometimes you're driving and you kind of space out and you realize that you meant to go to your friend's house, but you started driving to school, right? That's because your hippocampus kind of took over and it remembers how to do, right? What things look like. And you just sort of start driving that way, all right? You just start following that spatial path. Um, Maybe you know how to get to Valencia. If I tell you to drive to Valencia, you know how to get in a car and get to Valencia. But if I ask you to give me the directions to Valencia, sometimes you're like, oh man, what's that street called? Oh man, what's there? What's a land sign that I could think of? Because you can't, right? To tell me the directions, that's frontal lobe stuff. That's analysis and putting things into words correctly and etc. But the spatial movement, that's your hippocampus. You remember how to get to Valencia, and so your body just does it without you thinking about it too much. Um, Now, your hippocampus also helps with other kinds of memories. And those memories are actually located in your neocortex. If I tell me about your prom, what dress did you wear? What suit did you wear? What music were they playing? If you remember, those memories are actually located in your neocortex, in the wrinkly portion of the brain at the very top. But your hippocampus is still involved in that. Specifically, it's involved in finding it. Your hippocampus sends connections to your neocortex. And when you remember something and you practice that memory, then it strengthens those connections. And so it makes it easier for you to remember that specific event later because you've strengthened that connection. That's what studying in part is. When I tell you to study for something and you go over the topic, you go over the example, you go over the definition, you go over the question in the packet. Well, what you're doing is you're strengthening the connections between the hippocampus and the neocortex so that hopefully when you read the question in the test later, that the hippocampus can turn on that memory automatically because it's already strengthened. It doesn't have to find it throughout the neocortex. Um, Now, uh, if you damage your hippocampus, the main thing that's going to happen is you're going to lose your memory. If you've ever seen the movie 50 First Dates with Drew Barrymore, where she repeats the same day over and over and over again, what she damaged there was probably her hippocampus. Because without her hippocampus, she can't create new long term memories. There was another character in that movie that could only remember about 10 to 30 seconds. That's a real thing that does happen. And usually these people, the damage occurs in their hippocampus. If you know someone who smokes too much marijuana and they are always forgetting things, where are my keys? And their keys are in their hand. It's their hippocampus that is being affected. Marijuana, the chemical that makes you feel high, um, is similar in shape to a chemical that naturally occurs in your brain. Um, and we call those cannabinoid neurotransmitters. And so the THC can attach itself to the cannabinoid neurotransmitter receptors in your hippocampus. But because it's coming from the environment, it's just a marijuana smoke, then it turns on the hippocampus just sort of randomly. And so now it affects your memory. Also, if you know somebody who's much older and they're very, very forgetful, that also has to do with the wear and tear of the hippocampus. Specifically, people who have very difficult lives they're very stressful lives. Stress damages the hippocampus. Chemicals like uh, norepinephrine and cortisol will damage the hippocampus. And so, if you have a very difficult life, a very stressful life, when you're older, you're going to have more damage to your hippocampus than someone who had a very good life, a very easy life. And so, that's going to mean that this person is going to have more memory issues than someone who had a very easy life. Now, doesn't necessarily have anything to do with things like Alzheimer's. Sometimes people ask that question: is this related to Alzheimer's? Not necessarily. In Alzheimer's, there is specifically a type of plaque that builds on the neurons and then sometimes kills the neurons because it kind of builds on top of them. And so that can happen on the hippocampus, but that isn't related to the normal wear and tear of the hippocampus, which also creates forgetfulness. Um, Now, the character I chose is the librarian. When you go to a library and you ask the librarian for a book, the librarian doesn't have the book inside her. The same way the hippocampus doesn't have the memory inside the hippocampus. But the librarian knows where to find the book in the library. And so she can take you to the part of the library where the book is. And sometimes you could just give her a topic and she knows how to find a book that can help you with that topic because she knows her way around that library, just like the hippocampus. The hippocampus will help you find the memory in the neocortex to turn it on for you. Um, okay. Now, I'm not going to talk a lot about the thalamus, but your thalamus is this sort of egg shaped part of the brain right in the middle. And your thalamus is your operator. It helps send the signals to where they got to go. So, you'll get visual signals from the brain, from the eyes, and your thalamus says, "Oh, this is visual information. Send this to the occipital lobe." And you get auditory information from the ears, and your thalamus says, "Oh, this is auditory information. Send it to the temporal lobes." And so it's kind of like the operator that sends signals to where they gotta go. Oh, um, here you can see the thalamus a little bit better. You can see that there is one on each side in the limbic system, one for each hemisphere. Um, okay. Now, your hypothalamus is directly under your thalamus. That's what hypo means, just under. So I told you your thalamus is this X-shaped thing, and your hypothalamus is this little beak-looking part of the brain. And your hypothalamus is your master gland. It controls all of the other glands. And so, as a result, all of the hormones of your body. Um, and so, because it controls your hormones, it controls anything that has to do with hormones, homeostasis, your ability to maintain a stable balance in hormones, and then physiological responses like emotions, your body's physical emotions, not your mental emotions like, oh, I think I'm sad, but your body's response, muscle tension, how fast your heart's beating, whether you feel, sort of gross in your body or light, um, thirst, hunger, sleep patterns, a lot of your autonomic nervous system things. All of those things are controlled through glands, and so therefore they're controlled by your hypothalamus. An obvious version of this is puberty. When you are around 8 to 13, uh, your hypothalamus notices that you have enough fat built up in your body. And if you have enough fat built up in your body, then your hypothalamus will trigger the puberty. What it does is that it sends a signal to the pituitary gland via hormones. And then your pituitary gland sends signals to the ovaries if you're a lady, or it sends signals to the testes if you're a gentleman. And the ovaries release estrogen, which begin the process of puberty for girls, and the testes release testosterone and androgens, which begin the process of uh, puberty for boys. Now, my character here for the hypothalamus is like a CEO. If a CEO wants the workers to do something, it doesn't go find every worker in the company and tell them what to do. It sends a signal down. So the CEO might tell the CFO or the COO, and then the those executive managers will tell the middle managers, and the middle managers will tell the frontline managers what to do, and the frontline managers will tell the workers what to do. So it's this sort of cascade process of information. And that's the way your hormones work. Your hypothalamus sends a signal to one gland, that gland sends a signal to another, until the right hormone is released, and then the body does what it's supposed to do. Your basal ganglia isn't one spot. It's a few structures in the limbic system that work together. And specifically, they work together to create repetitive movements. Think about movements that are automatic that you don't think about. If you're driving, stepping on the gas and changing to the brake, sweeping, writing a word. As you're taking notes, you don't have to think, I need to write an A. How do I write an A? And then make the right. No, your body just kind of knows that. You think apple, and your hand just writes apple without you. Except that it's not really without you. Your brain is doing this. What part of the brain? Your basal ganglia. At some point, you mastered writing. And because you mastered writing, your basal ganglia can put certain movements on a loop. That's why I have a DJ here, because a DJ can put a track on a loop, or a small portion of a track on a loop, and uh, your basal ganglia can put a movement or a portion of a movement on a loop. Think about when you first learned to ride a bike. When you first learned to ride a bike, you had to think about a lot of things: steering and pedaling and balancing and where am I going. And at first, that was really, really difficult. But hopefully, you've mastered that skill. And now, if you get on a bike, you don't have to think about pedaling. You don't have to think about balancing. Your body, your basal ganglia, does that for you. And it frees your frontal lobe and your executive functions to do other things like drive to where you have to go, think about the directions, talk about to someone who's biking with you, right? Um, and so, because you can put certain behaviors on a loop, it frees your executive functions to think about something else. If you damage your basal ganglia, you're going to get messed up movements, delayed movements like lag. If you play video games, sometimes you hit a button and it takes a moment before your character does what you told it to do. Well, that very rarely happens to you in real life. You move almost immediately after you think about what you want to do. But if your basal ganglia was damaged, all of a sudden there will be lag between behavior and thought. You might get tremors and shakes, spasms, involuntary movements. Now, I want to talk a little bit about the neocortex. The neocortex is the part of the brain we mostly think about when we think about the brain. It's the wrinkly part on the top. And so I want to talk briefly about the lobes, and then I want to talk a little bit about some of the further divisions. So I want to start out with the lobes. Your occipital lobe is on the back of your head. Okay, it's your neocortex in the back of your head. You have two of those, one in your left and one of your right. And your occipital lobe controls visual information. You'll notice here that I chose a digital producer, right? Because it's your occipital lobe that draws the picture that you see in front of you, right? When you're looking out and you see your computer, your kitchen, your room, whatever, right? Your friend in front of you. Um, the picture that you're seeing is drawn by your brain. Our eyes send information to the brain, but it's not our eyes that draws the picture. You'll notice this. If you ever take a movie, let's say you turn on your camera in your phone and you walk as you as you are taking a movie, as you're taking a video, when you play the video, you'll notice that your video bounces as you walk, but that doesn't happen when you are just seeing, right? Your brain doesn't do that to you. That's because your eyes send the right information, but your brain just paints a still picture in front of you. And so it paints, so it doesn't have to take in account the constant movements. Um, it's also why sometimes you see things that aren't there. Sometimes your eyes might sense something that's a little distorted in the periphery, or maybe it's dark out, or maybe you drank a little too much, or you've taken a drug, and now your brain paints in something that's not there at all, a monster. Maybe if you're taking a drug, you might see a monster that's not really there. It's because your brain painted in a monster. And even though your eyes don't see that, uh, your brain still painted it in. And so you see it. You might have also noticed every once in a while, you're looking for something, let's say in your room, and you look for it and you look for it and you look for it and you don't see it. And then you come back a few hours later and it was right there. And you go, how didn't I see this? It was right there. Again, it's because your eyes play a part in creating vision, but they're not the most important part. The most important part is your occipital lobe, who draws the picture. And so while you were looking, even though your eyes were clearly picking up the information, your brain never painted it in. And so you didn't see it right in front of you. If you damage your occipital lobe, obviously you're going to have visual problems, problems locating things in the environment, hallucinations, inaccurately seeing objects, things like word blindness might occur where you can't think of the right word, um, things like that. Okay. Now, your temporal lobes are on either side of your head, kind of right above your ear, or I should say, right behind your ear. And you can see it there on the spinning brain. Obviously, you have one on either side. Um, your temporal lobes control hearing. If right now, as I'm speaking to you, it's your temporal lobes that can hear the cadence of my voice, how loud or high or low or raspy or pitchy my voice happens to be. Um, uh, when we talk about understanding language, right now I'm speaking to you and you don't just hear the sounds I'm making, you understand those sounds as concepts, as a meaning. And only one of your temporal lobes can do that. And that is your left temporal lobe. You can hear with both uh, your temporal lobes the cadence, the loudness, etc. But understanding language only exists in your left brain, and specifically in the part that we call Wernicke's region. In your right temporal lobe, you have another part called the fusiform gyrus, which helps with faces. If you were to damage your temporal lobes, obviously you would have a problem understanding words, verbalizing or identifying objects with words. The character I chose here is Mel Gibson in the movie What Women Want. I think there's a new movie called What Men Want. And in that movie, uh, Mel Gibson can hear women's thoughts, right? So hearing women's thoughts, that would happen in the temporal lobes, even though for him it has nothing to do with his ears. Um, the temporal lobes are the part of the brain that hears and creates the meaning and sound. All right. If you were to put your hand in front of your forehead or on top of your forehead and just spread out your hand as far as possible, this is your frontal lobe. If there's a part of the brain that's you, this is the part of the brain that's you. This is your personality, your hopes and dreams, your goals, your ability to have self control, your ability to move your body voluntarily, your ability to speak, okay, problem solving, perception of self, impulse control. This is all your frontal lobe. If I were to damage your frontal lobe, there is a good chance that you would no longer be you. You wouldn't think like you wouldn't feel like you. Uh, Other people would recognize your face, but they would not recognize your personality. And they would say things like, that is not Jenny anymore. That person is no longer the Jenny that I used to know. Um, if you were to, if you, depending on which part of your frontal lobe you damage, you might also cause paralysis. For example, if you damage your somatosensory cortex, problems with self control, especially if you damage your prefrontal cortex or your anterior cingulate. Changes in personality also would be part of your prefrontal cortex and anterior cingulate. Because one of the things your frontal lobe does is it controls your limbic system. Your limbic system without your frontal lobe is very animalistic. It would be angry and sexual. Um, it would be maybe even violent, hungry all the time. It would have a hard time focusing and paying attention. And so your frontal lobe comes in and it controls that. Think of as a, a horse rider or a chariot rider controlling the horse. Uh, all of a sudden, your frontal lobe controls your impulses and then can guide them the way that it wants them to. The characters that I chose here are Pinky and the Brain, because first of all, they're smart mice. And even though one of them is smarter than the other, even Pinky is quite smart. He can speak and he has executive functions and they have goals. They want to take over the world and they have unique personalities. Pinky is very caring and he cares a lot about Brain and his emotions. And Brain, on the other hand, is a little bit more cold and calculating. Either way, their personalities are highly controlled by their frontal lobes. Um, Now, if you were to put your hand on the top of your head towards the back, that is your parietal lobe. And your parietal lobe controls the sensation of touch. Right now, if your shoes are a little too tight and you can feel that, if you pass your hands over your shirt and it's soft, or over the table and it's hard, maybe something is rough versus smooth, that sensation of touch, that's your parietal lobe that does that. There's a specific part of your parietal lobe that helps you to determine that. Now, there's another thing your parietal lobe does, which is the sensation of passing time. For me, I've been doing this video and it feels like it's been like 5 minutes from when I started. But if you've been listening, especially if you're not very interested, it might feel like I've been here for a few hours already. Um, that's because I am in flow and I am very focused on what I'm doing, time feels like it's going really fast for me. Where as for you, because you're trying to pay attention and you're not sure when it's going to end or what I'm going to talk about next. And again, if you're not very interested, it feels like time is dragging on. So there's another part of the brain that gets affected with marijuana. Sometimes when people smoke marijuana, time seems to get slowed down. That's your parietal lobe that's being affected there. If you damage your parietal lobe, you're going to have problems with recognizing parts of your body. For example, if I tell you, touch your elbow, you might not be able to grab your elbow correctly. Or if you do, or if I touch your elbow and I ask you, what part of your body am I touching? You might say, my thumb. Because your brain now doesn't recognize your body correctly and it doesn't know which part is sending the right signal. My character here is the Flash. You could imagine that as the Flash is running, you could feel the wind on his face, the ground on his feet. But also, if the Flash runs fast enough, he can time travel. And so the Flash can feel the world around him, he can feel the speed force, but he can also control time, or at least time travel, kind of just like your parietal lobe. All right. Now I want to talk about just a handful of divisions, smaller divisions of the brain. And so I want to talk here about your somatosensory cortex and your motor cortex. Your motor cortex is in your frontal lobe. You can see here is your motor cortex, and your somatosensory cortex is part of your parietal lobe. But these two parts of the brain work together to uh, have movement and sensation work together. Specifically, if I were to grab a cup of soda that's filled, well, my somatosensory cortex would help me understand that the cup is heavy. And so, therefore, it would send a signal to my motor cortex to hold the glass tighter, right? Because my motor cortex controls the movement of my hand, while the somatosensory cortex feels the sensation of touch. Maybe my cup is too cold, it has too much ice, and after a while, it starts to hurt my fingers because the ice is too cold. And so my somatosensory cortex will tell my motor cortex to put the glass down. And so there's always a back and forth between these two. And another important aspect of your motor cortex and somatosensory cortex is that they both have what we call point to point mapping. That is, the part of your brain that moves your pinky is the same part of my brain that moves my pinky, right? They all, your brain essentially moves your body in the exact same way that my brain moves my body. There are exceptions to that. Maybe you're a great dancer and you devote a slightly larger portion of dancing to your knees, or excuse me, of your brain to your knees. And because I don't dance, well, I just don't use my knees like that. And so I devote less space in my brain for my knees. Um, uh, but there are certain parts of your brain that we just use or that we have to devote a great deal of space for. For example, your hands. You use your hands for a lot of things: holding a pencil, typing, punching, I don't know, grabbing groceries, just all types of things. And so you have to devote more space in the brain to have all of that programming of how to control the hand. On the other hand, uh, my back is very large compared to my hand, but I devote very little space to my back. If you look at the picture here, you can see the hand is very large. That's because we devote a large part of the brain to the hand. But over here for my torso, it's just a very small portion of my brain devoted to my torso, and even smaller for my back specifically. That's because I don't use my back. I can feel it, but I don't have the need to move it in very specific ways, especially with the skin. Um, and even the muscles there are used very specifically. There's not very big movements. Now, let's say you're a gymnast and you do use your back to jump from one uneven bar to the other. Well, all of a sudden, you use your back in a more complex way than I do, and so you would devote more space to that than I do. Now, when we talk about language, language exists almost entirely in your left brain. And there's a few parts that help you with language. In your frontal lobe, you have Broca's region. And Broca's region helps you to create language. Right now, when I'm speaking to you, uh, I am using Broca's region to find the right words and say them out of my mouth. But also, if you're writing me an email or you're writing down notes, you still use Broca's region to find the right words and to think about the right concepts to write them down. If you use, if you write or speak in sign language, well, even though you're not using your mouth, you still use Broca's region to sign and to find the right words, etc. In your temporal lobe, you have Wernicke's region. And I know it's spelled Wernicke's with a W, but it's Wernicke's region. And Wernicke's region helps you to understand language. Right now, as I'm speaking to you, uh, you aren't just hearing sounds. The sounds I'm making mean words to you. And they not only mean words, they mean concepts and ideas. And that is Wernicke's region that does that. If I were to damage, or if you were to damage your Wernicke's region, you would not be able to understand my words. You would still hear the cadence of my voice and the loudness and how pitchy or deep my voice is, but you wouldn't hear the words. The opposite with my Broca's region. With Broca's region, if I damage Broca's region, I would still be able to understand you. But when I spoke to you, I wouldn't make words. I would just make sounds to you. Um, uh, Now, in the parietal lobe, you have your angular gyrus, and your angular gyrus helps you bring a lot of information together so that you can read information from your occipital lobe. When you read, there's words on a piece of paper that you're seeing. Well, that's coming in through your occipital lobe and it gets to your angular gyrus, and you have to find the right words. You have to find the right words in your Wernicke's region, and you have to be able to create language uh, from Broca's region, and then you have to be able to understand the concepts, the larger concepts of what you're reading, and that's going to be other general things or general parts of your frontal lobe and your parietal lobe, and all of that comes together in your angular gyrus, which you can see here is labeled as reading comprehension in that yellow portion in the parietal lobe. If you were to damage this, then you wouldn't be able to read or read as well. In fact, what we find is that um, people who have reading comprehension problems often have issues with their angular gyrus or the connections to their angular gyrus. You can damage these in a lot of different ways. If you have a stroke to a specific portion of the brain, you might damage it. You might damage Broca's region or Wernicke's region or your angular gyrus. Or maybe you don't learn, right? If you live in the jungle, let's say your parents misplaced you when you were 2 years old and you lived in the jungle by yourself and I don't know, some wolves raised you, well, you would never develop your Wernicke's region correctly. And so, if as an adult we found you, humans found you, we would never be able to teach you language. And so, uh, I might be able to teach you to say water when you're thirsty or food when you're hungry. But this conversation, this thing where I'm just like saying words to you and you just understand what I'm saying, that could never happen because the Wernicke's region didn't develop correctly. Sometimes people get really upset with this because it means that Tarzan could never happen. For Tarzan to have occurred, right? You leave a kid in the jungle, he must have already been like 8 to 10. Um, Otherwise, he would have never developed language So you couldn't leave Tarzan as an infant in the wilderness. Um, Let me tell you one more thing about Wernicke's region. Uh, your dog, sometimes you tell your dog that you're going to go for a walk, and he gets really happy, and he'll go grab his leash and go to the door because he knows what you mean when you say walk. He also knows what you mean when you say bath, and he runs underneath the bed because he understands you. And what part of your dog's brain is your dog using when he hears the word bath or when he hears the word walk? Wernicke's region, just like you. The difference is that your Wernicke's region is very thick and your dog's Wernicke's region is not very thick. Ours is just more highly developed. Now, what you're seeing here is your fusiform gyrus. Now, remember, your fusiform gyrus is only in your right brain. But if you look at the picture moving there with the brain, you see that the gyrus here is underneath the temporal lobe. Well, that gyrus in your right brain is called the fusiform gyrus. And specifically, what it does is it helps you to see faces. Now, you might be thinking, wait a second, I thought the occipital lobe helped me to see. And you're right. Your occipital lobe is able to create the picture of the eye or of the lips or the ears, but it's your fusiform gyrus who brings all of that together, all of those many pieces to make one whole face, one thing that we call a face. If you damage your fusiform gyrus, then you can't see faces anymore. Some people claim that they see a blur or just the different parts of the face just incorrectly put together. These people cannot even see their own face in the mirror. Now they can recognize you other ways. They can recognize your voice or how you walk or how you dress, maybe even your hair or your hairstyle, but they can't see your face. Now, your fusiform gyrus does other things too. And more specifically, what it does is it recognizes things that have visual mastery. We all have a friend who, like, we'll see a car and we're like, oh, that's Tom's car over there. And you're like, how do you know that that's Tom's car? Well, your friend knows that because your friend uses his fusiform gyrus to recognize cars because they have visual mastery. They probably know a lot about cars. They know the different makes and models and colors and things like that. And so then they're able to use their fusiform gyrus to pick out different cars. Um, Another example is if you don't know anything about cars and you open up the hood of a car, well, it looks like nothing. It looks like just metal and pipes and gears and belts, just like nothing. But if you learn about cars and you practice on them, well, all of a sudden, one day you're going to open up that hood and it's not going to look like a mess. It's going to look like an order. And you're going to be able to find the radiator and you're going to be able to find the engine or the oil, something or other. You might have noticed that I don't know anything about cars. It is your fusiform gyrus that helps you with that visual mastery. How can we show this? Well, if you look at those little purple things on the picture, on the slide, that's part of a study. And in the study, they would show people these little purple blobs, and they would say, this little blob is Tom, and Tom is the king. And this little blob is Susie, and Susie is the princess. And this little blob is Joey, and Joey is a mechanic. And then they'd show you a bunch of these, and then they'd show you one that you have already seen, and who is this? And of course, at first, you're like, no, I don't know, because they're just little blobs that don't mean anything to you. But then they would tell you who it was again. And as they're doing this, they are taking an analysis of your brain, MRI, or some other way of uh, seeing the activation of your brain. Um, as they keep on showing you these purple blobs, eventually you're going to start to recognize them. And you're going to be able to tell me that this one is Tom the King or Susie the Princess. And you know what happens in the brain when you start mastering that? We see the fusiform gyrus light up more. Because as soon as you've developed mastery, your fusiform gyrus takes a hold of that. And now you stop seeing the blob and you start seeing Tom the King. Okay. In my character here, I chose Blank Face from Dick Tracy because he doesn't have a face. Okay. Now, your corpus callosum is the connection between your left brain and your right brain. You might have heard that you have a left brain and a right brain. And your left brain and right brain mostly do the same thing, right? Your left brain controls the right part of your body. For example, your left brain controls your right hand, and your right brain controls your left hand. But there are things that are specific to one part of the brain or another. I mentioned a few. Language occurs in the left brain. Um, uh, Visual recognition of faces occurs in the right brain. And so your left brain and your right brain have to talk to one another. And how do they do this? Through what we call the corpus callosum, which is a bundle of nerves that uh, uh, sends information from the left brain to the right brain. Now, um, if you were to damage your corpus callosum, then your left brain and your right brain wouldn't be able to talk to one another. Now, this is rare. Some people are born without a corpus callosum, but usually what happens is that surgery is done to destroy the corpus callosum. And I'm going to go into that in just a moment, but let me just tell you my character here, which is Cat Dog, because Cat Dog has two sides, a cat and a dog, and they're connected by that little middle portion by their body. Now, um, when you get a chance, please watch the video that I posted about split brain research. In this video, you're going to see Dr. Mike Gazzaniga, who is a brain specialist, and he specializes in determining the differences between what happens in the left brain versus the right brain. And the other gentleman, by the way, Dr. Gazzaniga is the gentleman to the right. The gentleman in the front here, in the left of the photo, is Joe. And Joe does not have a corpus callosum. Why? Because he got seizures. And what a seizure is that sometimes a a portion of the brain, some neurons in the brain just start to fire randomly. And so it's like a little electrical storm. A seizure can be mild and localized. And a mild and localized seizure might look like someone spacing out. They might be talking to you, and mid sentence, they'll stop talking and stare out into the distance. And then they'll kind of just come back, right? But if that electrical storm continues to fire, right, the neurons keep on making the next neurons fire. Well, if it gets to the corpus callosum, then that seizure will get to the other side of the brain. And a very severe seizure like that could get someone to fall to the ground. They might thrash on the ground, hurt themselves. They might thrash their arms and end up hurting somebody else. And so there's a lot of ways to control seizures, including medication, different types of surgery, even interesting gadgets like they will attach a button with an electrical cord to your vagus nerve, literally inside of your body. And when you feel a seizure coming on, you hit the button, and that button has a battery. It sends an electrical signal literally to your vagus nerve, which will block the seizure in your brain. But if these kinds of things don't work, one of the things that they will do is that they will sever the corpus callosum. And in severing the corpus callosum, all of a sudden, the left brain and the right brain can't speak to one another. And so you'll notice that in the video, they'll show Joe a word, and they'll ask Joe, Joe, what did the word say? And he'll say, nothing. I didn't even see a word. And they'll ask him to draw it. And then he can draw it, even though he told you right now that he didn't see it. Well, what's happening is that Joe's right brain saw the word, and he can draw it with his left hand, because the right brain controls your left hand. But your right brain doesn't know how to talk, because your right brain doesn't have a Broca's region. And so your right brain uh, uh, sees it, it can draw it, but it can't tell you it sees it. The part of the brain that speaks is your left brain. And your left brain, or at least Joe's left brain, didn't see the word. And so when you ask him what was the word, his left brain, the part that can speak, goes, I didn't see anything, because it didn't. Now, for you or me, anyone that has a corpus callosum, that wouldn't happen. Because if my right brain sees a word, it can't say anything, but then it just sends it to the left brain via my corpus callosum. And then my left brain will say the word, whatever it was. Uh, Telephone, I think, was the word. And now, Joe doesn't have that ability because Joe doesn't have a corpus callosum. As I mentioned, watch the video. It is very interesting. Now, you might be asking yourself, how do we know this? How do we know that this part of the brain does this and that part of the brain does that? Well, because we've studied the brain, and we've studied it in a lot of different ways. One of the oldest ways to study the brain is through lesioning. And lesioning basically means that we destroy a portion of the brain. We don't do this to humans very often, although humans have gone through lesioning, sometimes by accident and sometimes because of unethical things that doctors have done. But we do it a lot to cats and mice and things like that. So what do? You take a cat and you have the cat do an activity, maybe go through a maze or problem solve an issue or something like that. And then you put the cat to sleep, you break its skull, and you destroy a small portion of the brain. You lesion a small portion of the brain. And then you put the cat back together, wait till it heals, and then you have the cat do the behaviors again. And whatever the cat can't do anymore, well, that part of the brain must have controlled that part of uh, that behavior. This is a lesioning study. Now, in humans, this usually happens by mistake, usually an accident. The gentleman you're seeing there is Phineas Gage. I always want to say Phineas and Ferb, but his name is Phineas Gage. And Phineas was a foreman in a railroad company. And what they did was they would put down railroad tracks. Well, there's a problem with railroad tracks that they have to be straight. And sometimes as you're putting down railroad tracks, there's a rock in your way. And so you have to get rid of it. So this is like 1800s. So what they did was they would manually drill a hole in the rock and then pour a TNT, like gunpowder, into the rock. And for whatever reason, they would put a metal pipe in the rock before they lit it and blew up the rock. Well, one day, as Phineas is putting the metal pipe into the rock, he rubs it against the rock the wrong way, and it sparks, and the rock blows up, and the pipe flies into Phineas's face. And you can see there the skull. You can see the pipe goes through his cheek, under his cheek, through his eye, and out through the top of his skull. It should have killed him, but it didn't. And so a surgeon was able to save Phineas. And as he pulled out the pipe, a portion of Phineas's brain came out. Phineas, before the accident, as I mentioned, was the foreman of this company. He was well respected. He was intelligent and had a lot of self control. People respected him. Um, but after the accident, he wasn't Phineas anymore. And people who knew him said that. They said, that's not the Phineas that I used to know. Because now he was violent. Now he was more sexually aggressive. He would get to work late and leave early. And so he would get fired from job after job after job. Eventually, he left his wife and kids and went to live in a different country. And today, we still have the pipe in in a museum. Now we know what happened to Phineas. His frontal lobe was damaged, and because his frontal lobe was damaged, he lacked self-control. We know this today. Most, not necessarily most, but at least most uh, prisoners, people in prison, who, especially those who have committed violent offenses, tend to have uh, brain trauma, usually to the frontal lobe. And the numbers tend to be like in the 80%. Um, uh, we know that damage to the frontal lobe tends to create uh, problems with self control and violence. Um, but obviously, we can't go around lesioning everybody and every animal. So there are other ways to learn about the brain. CAT scans. What CAT scans do is that they send X-rays through the brain, and they send X-rays through different angles, and then a computer makes a 3D image of the brain. An MRI does something similar, but with magnets. The magnets uh, affect the atoms in the brain, which then allow the computer to create an image of the brain. In an fMRI, um, they look for the blood. How much blood is, specifically blood oxygen, is being used in the brain. And so we are then able to not only see the image of the brain, but also see the activity of the brain. This is, depending on why they're sending you to get your brain imaged, they might use an MRI or a CAT scan versus an fMRI. What are going to be the different reasons? If they want to know whether you have damage, they might use an MRI or a CAT scan. If they want to see if you have a tumor, because what they're looking for is an image, something that looks wrong. But if what they want to know is how are you using your brain, well, now an fMRI tells me which part of my brain I'm using, which part of my brain am I using more or less, because now I know how much oxygen is being metabolized by the different parts of the brain. And sure enough, if one part of your brain is metabolizing more oxygen, that must mean that you're using that part of your brain more. PET scans are similar to those fMRIs, but instead of looking at oxygen, they look at glucose. They'll give you a little drink. It looks and tastes like Kool-Aid, but it has a little bit of a radioactive agent. And so when you take that drink, it it shows up in the PET scans, and now we can determine how much glucose your brain is metabolizing. And just like oxygen, if one part of your brain is metabolizing more glucose, then we know that that part of the brain is being used more than another part. An EEG machine or an electroencephalography machine also detects activation, but now not with an image. So you have all of these electrodes placed on your head. And what I'm reading now is how much voltage, how much electricity is your brain creating. And by determining that, I get a readout, like a wavelength readout, as to how much activity that part of the brain is using. We use EEG machines often in sleep studies and things like that, so we can see if your brain is going through the right motions, the right levels of sleep. Now, I can also do things like brain stimulation. I can drill a hole in your skull and put an electrode in there. And with an electrode, I could do both things: read it, have you do a task, and see whether that neuron fires, because my electrode will tell me if that neuron fire. And I can do the opposite. I can send an electric shock into your brain and see what happens with that. Now, um, you can do this to a cat or a rat. You might not think that's right, but you can do it to them. But there's not a lot of humans who are going to let you drill holes into their head. And so there's another thing that you can do: a transcranial magnetic stimulation. That's the picture you're seeing at the bottom there. You can see that there's like a little wand, and it looks like there's a little 8 on it. That is a magnet. And the magnet there is able to be focused. And so it'll go through your skull without hurting you into your brain. And basically, what it does is that it turns off that piece of your brain for less than a second. It just sort of messes it up. Why would I want to do that? Well, let's say I have you do a task. I'll ask you, I'll tell you a story, and then I'll ask you, was that right? Did Susie do the right thing? And then I will put the transcranial magnetic stimulation to your brain and see whether or not you can do that mental task, or how you do it differently when I mess up that part versus when I don't mess up that part. And what we find is that we can determine which part of your brains you do to do what. Now, if I were to put this in a part of your brain that doesn't do analysis, but that controls your body, let's say to part of your motor cortex, then you wouldn't tell me that you think anything. You would just move your body. Maybe your fingers would twitch, or your knee might spasm. Okay, so this is yet another way that we can study the brain. All right, guys. Um, this is the end of video 2. We talked about the nervous system, the brain, and how we study the brain. Feel free to contact me. And remember that I have Zoom sessions that are not required. But if you have problems doing the packet, if you didn't understand something, or if you have questions about the quizzes, feel free to stop by and I will answer those the best that I can. I hope to hear from you soon. Have a wonderful rest of the week. Bye bye.